Okay guys, so in this video I want to talk about min-max problems for multivariable calculus. So for that, let's just review how we were doing like this kind of problems for calculus 1, and then we're going to generalize those methods to calculus to multivariable calculus. So first, let's sketch some function f of x. Then for that function, I want to find my local mean and local max. So first, we can observe that for this particular function, we're going to have one local max and one local mean. And you can observe that at point x0 and x1, our slope for our function is going to be equal to 0. So in other words, to find the possible candidates where we're going to have our local mean or max, we need to find for which values of x the slope of our function is going to be equal to 0. But in this particular case, we're going to have just 2 points x0 and x1. For as our second step, what do we need to do? We need to check concavity. And why do we need to check concavity? Because if we, for example, are going to take y is equal to x squared, then you can see you're going to have one critical point x0, and your y2 prime is going to be equal to 2, or in other words, is positive. And that means that at that point x is equal to 0, we're going to have a local minimum. So in other words, if we're going to generalize that, we're going to have a local mean if our second derivative is positive, and we're going to have local max if our second derivative is going to be negative. So let's right now keep those two steps in our mind, and let's generalize them to multivariable functions. So first, let's just sketch some multivariable function, and in this case I'm going to take a paraboloid which is going to point down, and you're going to observe that for that paraboloid we're just going to have one local maximum. And at our local maximum, if before we had that our tangent line was parallel to x-axis, then for our multivariable calculus, we're going to have that our tangent plane is going to be parallel to xy plane at the critical point. So to find our critical points, what do we need to do? We need to check that rate of change in x direction is going to be 0, and the rate of change in y direction is going to be 0. Or in other words, that's our slope in x direction and in y direction are both going to be 0. So to figure out what is going to be our critical points, what do we need to do? We just need to find our derivatives and solve the system for x and y. And again, our second step is going to be just check the concavity, and you can see that for our previous example we had that we have second derivative is positive or negative. But what we're going to do for multivariable functions when we have function f of xy? So in general, we're going to have three possible situations. So we're going to consider paraboloid that are going to point down, paraboloids that is going to point up, a surface that looks like a saddle. So let's take the first surface, and we can see that if we're going to consider the section along x-axis, whose concavity, or in other words, a second derivative corresponding to x, is going to be negative. If we're going to consider the corresponding section along y-axis, then we can see that we're going to get the orange section, whose concavity is also negative. And let's do the same thing for our second surface. In that case, we're going to obtain that our concavity for green section and for the orange section are both going to be positive. And if you're going to do the same for the third surface, then here's going to be something interesting. This green section in this case is going to be negative, as our parabola is going to point down, but the concavity of the orange section is going to be positive, as our orange section is going to point up. And then let's just do something interesting. Let's consider our critical points, and for each of the surface I'm going to have just a new critical point, and let's multiply our second derivatives. Then you can see that for the first surface the product of second derivative is going to be positive. For a second surface is also going to be positive, but for the third surface is going to be negative. And the interesting observation that for the first surface our second derivative is negative, which gives us maximum. For the second surface our second derivative is going to be positive, which is going to give us minimum. But for the third one we're going to have a saddle point. Why a saddle? Because in one direction we're going to have local max, but in another direction is going to local min. So in other words, our point is going to be unstable. In general, if we're going to have some critical point x and y, since we have 4 second partial derivatives, then I need to introduce the new kind of object, and that object I'm going to call d in terms of x and y. And I'm going to define as a product of f of x, f of y, and minus f of x partial y squared. And then let's make the table, where I'm going to consider d positive is equal to 0 and negative. If d is positive and f of x is positive, then xy gives us a local mean. If second derivative corresponding to x is going to be negative, then that point is going to give us max. When d is equal to 0, we cannot say it's undefined. And when d is negative, we're going to have a saddle point. And let's do one really simple small example. Let's consider the function f of xy, which is equal to that polynomial expression. So our first step is to find the critical points. For that, I'm going to find first derivative corresponding to x and first derivative corresponding to y, and set it equal to 0. After that, I need to do a simple algebra simplification, which is multiplying both equations by -1 and also dividing both equations by 2. You can see if I'm going to do that, I'm going to obtain just 14x plus 2y plus 2 is equal to 0, and 2x plus 6y plus 6 is equal to 0, or in other words, 7x plus y plus 1 is equal to 0, but then I can solve for y. So y is going to be equal to negative 7x minus 1, and then I'm going to take that y and plug in into the second equation. So what I'm going to obtain after that, I'm going to obtain that negative 20x is equal to 0, so x is equal to 0. And if I'm going to plug in that x back to my y, then I will figure out that my y is equal to -1. So 0, -1 is going to be a unique critical point. Then our next step is check concavity. So for that, we need to find f of xx, f of yy, and f of xy, and plug in them inside my new object D. So f of xx is going to be -14, f of yy is going to be -6, and f of xy is going to be -2. And if I'm going to do a simple arithmetic manipulation, then I can see that I'm going to have 14 times 6 minus 4, which is obviously strictly bigger than 0. So that means that my D is strictly bigger than 0. So a unique critical point 0, -1 is going to give us a local min.